Assalamu alaikum and good evening to all students. Today's topic is about the Introduction to Lyotropic Liquid Crystals, Part 1. This presentation slide is in PPS format. You can convert this PPS format back to PPT, which you can print and may be easier for you when you do a revision. For those of you who prefer to watch in video form, you can convert the format to MP4. Before I continue with today's lecture topic, I would like to remind all students about the detailed planning and schedule for my part. Due to technical problems during my first lecture, I urge all students to look at my teaching planning that you can get at Spectrum. Please provide feedback if there are any objections, especially regarding the summative assessment, which I had planned to be conducted in the 7th week. You will be given 1 week to prepare it. This planning can be seen in the file titled Timetable and Related Topics for Dr. Rusna. I have checked and only 21 out of 27 students have seen this file. The second way to get information about the detailed teaching schedule is in the first lecture slide called Introduction to Liquid Crystals. Through the review, there are 12 students have opened this file and most of them have already seen the file Timetable and Related Topics for Dr. Rusna. Only 2 students have just seen this plan. In total, 23 out of the 27 students who registered were aware of the schedule and planning. To students who have not seen this plan, please check it out immediately. If I don't receive any suggestions by today, I assume that all students agree with the plan. For today's class, and all asynchronous lectures, attendance will be taken from the report logs in Spectrum. Please open the file in Spectrum according to the schedule for the attendance to be counted. There are 5 learning objectives related to lyotropic liquid crystals that students need to master. All these 5 are for lectures Part 1 and Part 2. After we finish the topic of Introduction to Lyotropic Liquid Crystals, students should be able to understand what are lyotropic liquid crystals, able to compare thermotropic and lyotropic liquid crystals in terms of their condition of phase formation and molecular design, mesogenic design for lyotropic liquid crystals, able to describe the polymorphism, self-assembly, of amphipholic molecule in solvents, able to sketch the molecular arrangement in micelle, hexagonal, nematic and lamellar phases. These learning objectives are only part of the course learning outcome, CLO, explain the driving force for the self-assembly of lyotropic liquid crystal phases and their biological significance, the first CLO for my part. I assume that many of you assume that all the solids may be arranged in an orderly repeating pattern. It seems like everyone knows things are solid at certain temperatures. If you heat them up, they will become a liquid. The temperature at which a solid becomes a liquid is called its melting point. By thermal heating, a crystalline solid will always melt into a liquid above the melting point. But, that was not the case for liquid crystalline materials. For liquid crystalline materials, it will melt into liquid crystalline above the melting point. In liquid crystalline phase, a fluid phase in which a liquid crystal flows and will take the shape of its container. It differs from liquid that there are still some orientational order possessed by the molecules. The molten material will not appear clear but turbid even if it has been in liquid form. When the temperature is raised further, at a point where the turbid liquid has turned into a clear liquid, that point is called the clearing point. The molecules in the liquid now do not have orientation and positional orders, but are held together by weak intermolecular forces. Therefore, for a material that exhibits the properties of a liquid crystalline, will show 2 transition temperatures when heated from solid to liquid. As I have informed before, liquid crystals can be divided into thermotropic and lyotropic liquid crystals. Please observe the example given as shown on the slide. The design of the 2 compounds is different. For thermotropics, it is rod-shaped and rigid, for example calamitic mesogen. Whereas, for lyotropic, the compound design must contain both hydrophobic as well as hydrophilic parts in the same compound. Compounds that have this property are called amphipholic compounds. This slide shows some examples of the design and how the molecules are arranged. On the left is a disc-shaped molecule. It can form a hexagonal or nematic phase. The middle one is a molecule that is entirely curved in shape. This mesogen is called banana-shaped. And the liquid crystal phase that exists is smectic. To the right of the slide is a rod-shaped molecule. Such molecules will show a smectic phase or a nematic phase. There are types of smectic phases that exist. You will learn more in depth in class with Dr. Etheu. In Lyotropic liquid crystal, we also have a material whose molecular design is the same as discotic. I will introduce it to you little by little. This slide shows the differences between thermotropic and lyotropic liquid crystals. First, the thermotropic is able to display a liquid crystal phase without the presence of a solvent. For lyotropics, the liquid crystal phase is exhibited in the presence of a solvent, whether polar or nonpolar solvents. There are mesogens that show thermotropic and lyotropic properties as well. For example, mesogens called glycolipids exist in the liquid crystal phase without any solvent and at the same time show another liquid crystal phase when in contact with the solvent. Second, in thermotropic, the formation phase is induced by temperature. For example, cyanobiphenyl, 5Cb, undergoes a phase transition from a crystalline state to a nematic state at 24 degrees Celsius, and it goes from a nematic to an isotropic state at 35 degrees Celsius. In lyotropic, the phase formation is induced by temperature, concentration, salt. As an example, unethoxylated alcohols will form lyotropic liquid crystals at high concentrations. At the concentration of 50% and the temperature below 55 degrees Celsius, it exists in hexagonal phase, but when the concentration is higher, such as 70%, it will shows lamellar phase. Third, its molecular design. For thermotropic, it will be rigid organic molecules, while for lyotropic its design is like a surfactant, which is amphipholic and also chromonic. Fourth, the differences in terms of its microstructure. In thermotropic, we will know the smectic and columnar phases, while in lyotropic we will know phases such as lamellar and hexagonal. This is the first mesogen type that we will discuss in lyotropic liquid crystals. Amphipholic liquid crystals. The molecule used as an example is sodium dodecyl sulfate, SDS, or sodium lauryl sulfate, SLS, sometimes written sodium lauryl sulfate, is a synthetic organic compound. It is an anionic surfactant used in many cleaning and hygiene products. This molecule is an organosulfate in a salt. It consists of a 12-carbon tail as the hydrophobic part attached to a sulfate group, which is a polar head group, give the compound amphipholic properties. Therefore, in general, amphipholic liquid crystal is a compound which has two immiscible hydrophilic and hydrophobic parts within the same molecule is called an amphipholic molecule. Many amphipholic molecules show lyotropic liquid crystalline phase sequences depending on the volume balances between the hydrophilic part and hydrophobic part. I'll elaborate this part more in packing theory. The driving force for the phase formation are the hydrophobic effect, closest packing, and microphase separation. The hydrophobic effect is the observed tendency of nonpolar substances to aggregate in an aqueous solution and exclude water molecules. Controls the aggregation of amphiphiles. The term, closest packed structures, refers to the most tightly packed or space-efficient composition. Microphase separation is the term used to describe the hydrophilic and hydrophobic part within the same molecule. These three driving force causing the molecules to assemble spontaneously. This slide shows examples of amphipholic molecules. It can be non-ionic, anionic, cationic or zwitterionic. Specific examples and names are also given. This slide shows the phase diagrams of amphipholic molecules in general and concisely. The exhibited liquid crystalline phases are given in the form of symbols and their full names are provided in the table on the right. The right part of the phase diagram is when 100% of the water content is marked 1, and amphipholic molecules are added little by little according to the composition. In the condition, interface curvature equals 0, indicates no water. 100% pure amphipholic material content. The left side marked 0 indicates 100% nonpolar solvent content. Please see and understand this detailed description. This description will describe the parts with polar solvents, water, only. Because what is observed on a nonpolar solvent is the same, except that the surfactant is inverted. The content of water or other solvent molecules changes the self-assembled structures. At very low amphiphile concentration, the molecules will be dispersed randomly without any ordering. At slightly higher, but still low, concentration, amphipholic molecules will spontaneously assemble into micelles or vesicles. This is done so as to hide the hydrophobic tail of the amphiphile inside the micelle core, exposing a hydrophilic, water-soluble, surface to aqueous solution. These spherical objects do not order themselves in solution, however. At higher concentration, the assemblies will become ordered. A typical phase is a hexagonal columnar phase, where the amphiphiles form long cylinders, again with a hydrophilic surface, that arrange themselves into a roughly hexagonal lattice. This is called the middle soap phase. At still higher concentration, a lamellar phase, neat soap phase, may form, wherein extended sheets of amphiphiles are separated by thin layers of water. For some systems, a cubic, also called viscous isotropic, phase may exist between the hexagonal and lamellar phases, wherein spheres are formed that create a dense cubic lattice. These spheres may also be connected to one another, forming a bicontinuous cubic phase.